Okay, so for our second talk, it's also about monitoring in data centers, but with microsecond level accuracy. So our speaker, Hao Zheng, is a fourth-year PhD candidate from Nanjing University. His research interests include network measurement, high-performance simulation, and programmable networking. He is currently on the job market. If you have a job, contact him.
Thanks for introduction. And my name is Hao Zheng. It's my first time to give a presentation in English, so I'm a little nervous now. Hope you can forgive me if I make something not clear, and in that case, you can make a discussion with me after the presentation is finished. So our topic today is microsecond level monitoring in data centers. Let me give you some background. We know that network monitoring is a widely deployed and in general monitoring system serves two primary purposes. The first is application traffic management. Right? We use traffic monitoring tools like NetFlow, SFlow to capture some important flow metrics such as flow counters, flow rates, flow completion times, heavy hitters, and so on. And the second part is network status or event detection. That means we use some tools like SNMP, GFC to collect network status, network events, especially congestions, and caused by incast, load imbalance, and others. So our topic today is the time granularity of the network monitoring system. What is time granularity? The time granularity is the resolution or interval at which network measurement data are collected, determine accuracy and resource cost of the monitoring system. Let me give you an example. In coarse grain time granularity, we use the large operating window to measure packets. For each window, it covers a long span of packets, and we use the counter to measure the how many packets or how many bytes in the window. And in fine-grained time granularity, we use much more smaller operating windows, and it generates more counters. So the problem here is that currently there is a gap between the monitoring granularity with the activities in data center networks. The modern data centers have ultra-low end-to-end latency, measured in several microsecond timescale, thanks to the faster port speed and the switch chips. We equipped our host with RDMAs and user switch TCP, and we use techniques like hardware offloading. These techniques make our data center much faster now, but our current monitoring system is still at millisecond to minutes level, and it misses a lot of valuable information. What I mean is that our monitoring system now cannot fully control our networks now. So let me give you a case. There is a network, and suppose we use RDMA, and there are senders and the receivers. Suppose there is a congestion in the switch, and the receiver may say sender and will send a congestion notification package to the sender, and the sender will adjust or reduce its flow rates, standing rates. So because the RTT in the data center is in the microsecond level, right? So the rate change is also in the microsecond level. It brings up a question. If we are developing a new congestion control algorithms with some vulnerable hardware or software, if there is a poor performance issue, how can we debug our transport algorithms? It's a question. In simulations, it's quite easy to solve. If we use NS3, we can print anything in any time scales, and we can analyze the flow rates like this. We can plot the flow rate curves, right? We can analyze our system design or algorithms design. But in production networks, we only have millisecond to minute level flow measurement. And this coarse grained measurement can only provide an average rate. in the microsecond scale, so it brings less information, and it cannot help us to debug our transport algorithms. So our abbreviation is that microsecond-level network monitoring is necessary for current high-performance networks. There are some related works, and the first part is traditional monitoring systems, such as NetFlow. SFlow, it operates at the second to minutes level, and the second part is recent monitoring systems, such as the Trumpet, Florida, and Sketches. They work at the millisecond level, and yes, there are some microsecond level monitoring systems too, but our conclusion is that currently there is no network monitoring system that simultaneously supports microsecond level flow rate measurements at scale, and it can make analysis on congestion on command switches. Command switches, I mean, is like say unprogrammable switches. And we make some profiling on this topic task, and we found microsecond level monitoring do generate more measurement data. For example, if we refine a 10 millisecond level measurement to 10 microsecond level measurement, in this case, in the worst case, 10 millisecond counter is expanded to 1,000 10 microsecond counters. This is worst case, and in very average case, we do some evaluation on two typical workloads, which is mixed of long and short flows, and the data volume is increased by dozens to hundreds of times. So the biggest challenge is that how to reduce the significant memory and bandwidth overhead if you want to use the microsecond level monitoring. So before I dive into the design details, let me give you an overview first. We propose micromon or mMon. It includes three parts. The first part is that we measure in microsecond level flow rates at hosts. It's a per flow microsecond level lightweight and accurate flow rate measurement. And in the network, we detect network congestions. And the third part is we have an analyzer. In the analyzer, we collect microsecond level flow rates, and we collect congestion events packets from network. The event packets can tell us the network load status of our network, and if we are interested in a heavy congestion, we can replace the congestion by combining the flow rate information and the events context. So we can plot these curves, and we can analyze how the congestion happened and what's the impact. The first part is microflow measuring. Recall that our target is to count the number of packets or bytes of each flow at microsecond level windows, and there is the counter sequence because we are in the microsecond level, right? We have too much counters in the sequence. So the problem is how to reduce the counters, how to compress the counters. There are some Roman solutions. The first solution is can we use some traditional compression tools like LZW, Hoffman, but these tools involve complex computation and memory operations that cannot be implemented in the data plane. So we first need to transfer the uncompressed data to the control plane, and it make the PCIe as a bottleneck. And the second solution is we directly use some existing sketches, but these sketches do not consider the continuity and variability present in the sequence. So an ideal solution should have two requirements. The first is it should be a compressed unmeasured algorithm. And the second requirement is that we need to preserve the sequence features. So our answer is wavelets. The key idea is that we abstract the counter sequence as waveforms, and we compress the waveforms using wavelet transform theory. So there is a wave rate curve perspective of the counters, and we use wavelets. The first step is wavelet transformation. We use the Mara wavelet and to generate a set of child wavelets by scaling and translation. These child wavelets decompose the original curve into many wavelets, each with weights or coefficients. With the decomposition, we can know which part of the curve is important, which part are not important. So we can do some compression in this stage, and we can discard or drop some not important parts, not important in wavelets. And after we do the compression, we can reconstruct the original curve in the analyzer. Because we drop some wavelets, the regression may cause some errors. So the advantage of the multi-resolution analysis is that wavelet-based compression is that it has multi-resolution analysis. It can automatically capture the components that best characterize the curve from different time points and different scales. Although the wavelet-based compression is good, but it cannot directly use it in the network measurement. And we still have 3 problems to solve. The first is we need to simplify the calculation of coefficients. We need a strategy for coefficient detection, and we need to adapt the whole algorithm in an online and streaming fashion. Okay, we introduce WaveSketch. WaveSketch equipped the sketch with wavelet-based compression, and it is built upon a basic counting sketch with several rows of counters. But the difference is that each counter is not a simple counter, it's a wavelet counter. It has a bucket and several variables in the counter. The update process includes several steps. The first step is counting. It is very similar to existing sketches. If there is a package and we add the counters, when a window is finished, the counter is finished too, and we need to transform the counter with wavelet-based transformation. And we use hard wavelets here because it's the simplest wavelet. You can see the right side is a simple step function. So this function makes the calculation of the coefficients very easy. It is composed of simple addition and subtraction operations. After the transformation, they will gradually generate some coefficients. And in the compression stage, we select top K coefficients with a weight. So this is our strategy, and there is a weight because we need to minimize the reconstruction errors. We give a proof in the paper. If you're interested, you can read the paper. Finally, in a controller or analyzer, we can reconstruct the flows, curves if we are interested in. The WaveSketch has some good features. The first is that it is an algorithm with O1 update complexity. The second, it has a good compression performance with little construction errors. And we do include an extended version and hardware version implementation. Please see the paper for details. Let me show some use case of WaveSketch. The first is traffic analysis with WaveSketch. WaveSketch can tell you the rate curves over flow during a time span. So we need to input the flow ID and the T start, T end to the sketch, and the sketch can tell you the rate curve. So we can analyze some flow rates. The first example is we can analyze a TCP flow. It's a low throughput flow. During the microsecond level, we can see that there are many transmission gaps at the microsecond scale. So we can judge that it cannot provide sufficient data to link. It's not the network problem, it's just the host problem. The second case that we can observe how the RDMA flow is responsive to congestion and how the rate recovers after the congestion disappears. Thereby, we can verify in our congestion control algorithms. The second use case is congestion analysis with WaveSketch. After congestion happens, the first problem is how can we detect the congestion? A ready-to-deploy method is used in micromon. So we first detection the congestion by match and mirror the ECN CE marked packets. And maybe the sampling can cause, maybe the mirroring can cause some bandwidth overhead. So there is a sampling phase. we collect the congestion events. It contains flow IDs and timestamps. We put it into the wave sketch, and we can replay the congestion events and analyze its cause and impact. microMon is also compatible with programmable switches. I mean, we can use existing more advanced congestion detection solutions, but here we select a ready-to-deploy solution for existing data centers. We do some evaluations, and the evaluation shows that our flow rate measurement is quite accurate. It can improve accuracy by 3.5 to up to 57 times accuracy than baseline solutions. This is the average results on a workload. Involves many flows, so if we zoom in a single flow, we can see that the wave sketch can focus on the most dramatic parts and use this memory on smooth part, and the existing solutions are not sensitive to the rate change in seconds. So let me make a conclusion. microMon serves two problems. The first is microsecond level flow rate measurements at scale. The second is microsecond level congestion analysis. And our future work includes real deployment in production networks and find some character analysis. And the second is deploy the algorithm design further with more accuracy, performance, and reduce hardware resources. Thanks for your listening. This concludes my presentation. I'm glad to take some questions.
Okay, thank you. Yes, questions from the audience.
I'm Kun Qian from Alibaba Cloud. Very good question and very impressive talk. I have two questions. First, does Wavelets introduce loss in the prediction, in the precision?
Yes, thank you for your question. It's a good question. Wavelets do involve some recursion errors, but it has some good features too. The first is the average rate or the total bytes or total package is always right, but in some details flow rate curves, it preserves the most important part with the large rate changes, but in the smooth part it may involve some errors.
Okay. The second question is that when you combine the wavelet with the sketch, you need a window, right?
Yeah.
A time window to calculate the sketch. How to set this parameter and how to implement it in either the DPU or programmable switch?
Yes, it's a good question. And we gave a hardware implementation based on IMT architecture in the paper. So the time granularity is set to 8 microseconds, and it can be implemented in such a Tufino. So maybe you can read the paper for details.
Okay. The time window set should be lower than our desired granularity, time granularity, right?
The time granularity in the sketch is set to our design. It's just 8 microseconds.
Okay, equal.
Equal to it, yes.
Okay, thank you.
It may be smaller than our RTT.
Okay, thank you.
Hello, thank you so much for your talk. I'm Shayan Azizi from UNSW Sydney here. And my question was basically related to the previous point, and it's more like, so I got that your context is monitoring the rate and congestion control. But what if you want to do some telemetry that is sensitive to outliers, like getting maximums? So how does Wavelets behave in those scenarios, given its losslessness?
Sorry, I'm not getting your question. Could you repeat?
Yeah. So imagine you want to do network telemetry, and the parameter you're going to measure is sensitive to outliers to the actual value. So if I have got a large value, I just want to keep that. But wavelength is lossy, right?
No,
So-
Wavelet, thank you for the question. Wavelet will try to preserve this part because after we decompose the rate curve, this part has a higher weight, and we use the top K strategy to prefer to preserve this part. So the smooth part with this change, it will be discard or drop.
Yeah, thank you.
Okay, we have time for one more question.
It's from Chen from Princeton. Thanks for the talk. For your replace module and also the analysis module, is this online as well? Meaning, can you identify which flow contributes to the congestion online?
Yes, the network detection solution detects the congestion online, and it collects some packets information, and it contains flow ID and timestamps. But we analyze the congestion offline, but the detection is online.
Okay, thank you.
Okay, let's thank our speaker again.